they cannot do, for example, joins or run storage procedures, or like, maybe perform complex aggregation functions or arbitrary aggregation functions. So these decentralized storages, they do not allow you to perform sophisticated queries. You can use a blockchain to store your data and then query it, but that's probably will be really expensive if you want some kind of, good security. So probably storing a gigabyte of data in Ethereum, you will not be able to do that. And let's take a look at what approaches currently exist. So for example, if you have a decentralized storage and you have a client and the client wants to perform a query to the data stored on this decentralized storage, what could we do? Well, one of the pretty obvious solutions would be to transfer the required data to the client. This will work for the simple cases, but this will not really work for the complex queries, because complex queries such as joins will require you to just transfer too much data to the client. And ideally, we would like the client to be really, simple, thin, and really, we would like the client to not do much. Otherwise, I can just, install a full node to install my own server. And the second approach, as we already have said, what's the problem with the second approach? We could use a blockchain, but within a blockchain, you have just too many nodes that are performing those computations. And that's probably too much of redundancy. And this works if your problem is small. So if, for example, you have a 100 megabytes table, but if you try to put really large scale data, then probably replicating it to hundreds of nodes is a little bit of an overkill. So let me actually, before we go further, let me check if this thing has deployed. Okay, so that thing has deployed. So now we have a database, and I can open the web console. Okay. All right. So that's the SQL console for this just deployed database. And we can see that there are 4 nodes here. And we see that there are these nodes are connected with Tendermint. And each node has the block 2 here. You can see this height 2. And on each node, there is the same height. Height 2 here, height 2 here, and so on. And now we can try to execute queries. Well, the just created database is really empty right now, so I can try to create a new table. All right. What's that? Yeah. Oh, yeah. Yeah. How do I do that? Yeah. Okay. That should work, I guess, better. Okay, so I can say I want to create a new table, and the table with users. So I just click Submit Query. And we can see that the table was created. And here we see that the number of blocks in the Tendermint chain has increased by 2. Now I can try to populate this table and add a few more users in it. I've got 3 of these users, and I can add Sarah too. All right. So now you can try to execute SQL queries against this stuff. So I can say select star from users and just run this query. Okay, so we've got this table, and that's really simple. Any decentralized storage can do that. But I can also do the filtering query, so I can say select star from users where age is more than 20. You can do this as well in a decentralized storage if you build, if you kind of order your rows in the tree by the age. But the whole thing about this is that the filtering clause is completely arbitrary. I haven't done any indexing by the age field. So what I can do next, I can say, let's just calculate an average age of all users. And, well, this is like some auxiliary field, but that's the average age of users. And finally, let's have some more fun. I can say, I want to create a table of roles. And this table has the foreign key of the user ID, and I can add roles to those users. And now I can say, issue a really complex query. Oops. Okay, let's see. Which will involve joins. So I can do a join query and basically attach to each user the role. So basically, you can see that's a pretty much arbitrary SQL engine, but that which runs in a decentralized fashion. So in order to run this engine, you need to also perform computations. But before we get to that, I can also show how easy it is just like to send queries from the browser. So here, I can go to the developers console. That's the browser console. Oops. Actually, do you have Chrome, by the way, Alex? I don't know how to do this in the Firefox. Okay, maybe I can do debugger. So, okay, I've got it. I think I've got it. So I can say, for example, this. And I can put into the developers console. And I can now connect to this database from the browser. And this way, I have just created a new session. So I just said, connect to the database with the application ID 40, and I have put the Ethereum smart contract address here. And now, everything I can do, I can, for example, say, I want to select the average age of all users. Okay, and so we've got the result right here, which is 24.5. So you can see there is no need to run the like complex backend. You can just make queries from the browser machine, and that works. So how is it possible to run large-scale database in a decentralized network? So the way how we do it is that we use a hybrid approach here. So we think that without the computational engine, it's not really possible to run arbitrary queries. And what we basically do, we split all of the nodes in the decentralized network into few layers. And the first layer is the speed layer, which has database clusters. And these database clusters can be fairly small. So they can have maybe 4 machines connected with the BFT consensus, or 7 machines, maybe 10 machines. So they're not necessarily, super secure. It's because it's very few machines, that there is a high chance that those machines will be all, malicious. So in order to guarantee security here, we add a layer of the batch validators, or you can call them also fishermen, that are constantly monitoring the speed layer, and if they find that the speed layer has cheated and has provided incorrect results to the client, they kind of escalate the stuff to Ethereum, and malicious machines lose their stakes. And we also rely on 2 more layers. we use Swarm or Filecoin or some other decentralized storage as a data availability layer, and we use Ethereum as a, like the source of trust and the dispute resolution layer. So the way how stuff works looks roughly the following. The speed layer is really small, and usually a single database has, well, in our example here, we had roughly 4 nodes. And this speed layer, all of the nodes in the speed layer are connected with BFT consensus, and we use Tendermint, well, just because it kind of works. And each of the nodes in this cluster runs a WebAssembly virtual machine. So because we use WebAssembly, we are able to compile existing databases into WebAssembly, and we have ported this small SQL database called LlamaDB, and now we have almost ported Redis. And maybe soon we'll port also like SQLite or something like that. But what's more important here, that the client interacts only with this real-time layer. The client does not really talk much to Ethereum, doesn't talk to the batch validation layer, doesn't talk to Swarm. It talks only to the real-time layer. And the real-time layer takes the history of transactions, and every request that the client sends to the real-time layer is wrapped into a transaction and is then uploaded to Swarm. So say, for example, if I'm trying to make an insert query, then, well, it's a transaction. But if I'm trying to make a select, that's a transaction as well. So it will be, the results of this transaction will be later verified. So once the history of those transactions is stored in Swarm, it's stored in block by block there. So we have a transaction history, and we have a validation mechanism that allows us to take a fragment of transaction history, so basically take few blocks out of the transaction history, and then kind of replay them and verify whether the state changes that were made by the real-time database were correct. So here's where the validators pool comes in handy. So while the databases here, these guys are different for every developer. So if, say, for example, if Alice has deployed a database and Bob has deployed a database, this will be 2 completely separate BFT clusters. But the security layer is shared across the entire network. So there is really low chance to make a collusion between the nodes. So the way it works, each validator, or a fisherman, is chosen completely randomly from this validators pool. And then it replaces this transaction history segment and computes the new state. And it takes, the way it works, it basically takes the preceding state from Swarm, applies transaction history, generates the new state, and uploads this state to Swarm. So the real-time cluster does not upload any states to Swarm, the snapshot of the virtual machine state. This is done completely in the batch mode. And what's cool about this design is that this allows to have completely, to be able to completely randomly sample validators from the validation pool. So they don't really know each other, and they cannot collude. And also, each validator verifies the previous validation as well. So it can say, okay, if this validator finds that the previous validation was not correct, it can challenge it. Or if a validator finds that the real-time database results were not correct, it can also challenge them. And if there is a challenge, so basically 2 machines on the network do not agree on the computation results, then the verification game happens. And the verification game is a really simple way to resolve the disagreement about how the computation should look like. So imagine you have a WebAssembly program, and this program is as simple as this one. So you want, for example, to take 2 numbers in a function and add them together, and then just return this result. And let's say, for example, 2 machines are trying to execute this really simple WebAssembly code, but the bad machine got an incorrect result, and the good machine has challenged that. So how to like understand who is right and who is wrong? On the blockchain, you will probably have, you will probably have, I don't know, like 50% consensus. So if 51% of machines in the network say that 8 is the correct result, then it's probably correct. But what if I don't want to have too many machines in the network repeating the same computation? What can be done here is that these machines, they can find an instruction on which results of execution they do not agree. So in this case, so in this case, you see what happens. So first, the instruction get local reads the input and pushes onto the head of the stack. Then the next instruction get local A reads the next input and pushes it onto the top of the stack. And then the sum instructions reads first two elements from the top of the stack, sums them, and pushes the result back to the stack. So you can see that until the sum instruction, the stacks were completely the same for both machines, and they got different after the summation instruction. So what happens here is that you can take this summation instruction and just give it to the Ethereum smart contract, and you can take the input to this summation instruction and pass it into Ethereum, and then Ethereum smart contracts executes this instruction and says, well, that's like the left machine is the one who has gotten the computation correctly. So in this case, Ethereum is very computationally bounded, but your machines, like the validators and the database nodes, they have lots of power. They can be really powerful. So in this way, you do not overload a blockchain with your computation. You only rely on the fisherman. And now what happens here, let's say, for example, I have 3 validators in this, for this particular transaction history segment. If at least one of those validators is honest, it will cache all of the malicious activity that happened here. So it's much more efficient, well, I won't say consensus, but it is, much more efficient way to catch malicious activity on the network. And that's the difference. Let's say, for example, that our network contains 10% of malicious nodes. And we have set up, in one case, we have set up a 7 nodes BFT cluster. So the chance that more than 2/3 of the nodes in this cluster will be malicious is this one, just like almost 10 power minus 4. But if we, so imagine that we have a computational budget. So we have allocated a budget for 7 nodes, and that's the first option that we can do. But what if, say, for example, instead of this, we split this budget, and we split this budget into 4 workers BFT cluster, and we use also 3 batch validators. So the chance that in this case an incorrect transaction will go through is much lower, and it's lower almost by 2 orders of magnitude. That's because in order for the incorrect transactions to go through in this case, you need all 3 of those validators to be dishonest. So basically this allows you to get a much stronger security guarantees with less machines, and that's how we are trying to perform computations. And there are also other cool properties about that. So because these real-time workers, they carry the database all the time, they are really fast. So you have seen that I was able to perform a query and I've got an immediate result, and you probably won't get that fast in Ethereum, for example. But because those clusters are so small, it's possible that they will have, malicious cartels taking over them. So batch validators, they prevent those cartels from forming by penalizing bad actors. Well, I guess that's it about the architecture. And so far, we have released this. Oops, well, that's wrong. Well, so far we have released this Devnet version where we have only databases. So we have LlamaDB, which is SQL database, and we are waiting for Redis. And I believe somewhere later this fall, we will also release the security layer where we'll have the shared validators pool, verifying the entire network, like the history of all transactions in the network. And after that, we'll also have the incentivization layer. So like every node will be forced to have a stake, and if it misbehaves, then the stake will be slashed. But if you guys are curious, you can try the speed layer right now. You can just go to this. I have it here, right? No. Well, you can go to the Dash Fluence network and just play with it. Or if you are interested into the more foundational stuff, you can go to our GitHub repository, or you can take a look at the paper and try to see, like, to find bugs in there. And that's it, I guess. And thanks for your attention. Mm-hmm.
Suppose you're presenting in front of Tim Cook of Apple computers.
What's that? Mm-hmm.
Suppose you're presenting in front of Tim Cook of Apple computers. Mm-hmm. What problem does this decentralized database solve for Apple computers? Mm-hmm.
So what we are trying basically to do, we are trying to solve. So here's the thing: in the blockchains, the economy is really like they are supposed to serve financial data a lot, right? So you can transfer in Ethereum, you can transfer millions of dollars between different accounts and have lots of security. But sometimes you don't really need that much security. Like, say for example, what if I'm trying to build a game on top of decentralized platform? I probably don't really need that much security because I'm not like transferring millions of worth. But I still want to basically give my players confidence that the game will not change the rules. So I can deploy this game into decentralized platform, but now I need some kind of a database that will store the state about the players. And that's the design which basically trades off security for performance and cost efficiency. So it's like a little bit less secure than Ethereum, but much more, I would say, performant. So that's, I guess, like what we are trying to solve here. Cool. Mm-hmm.
So imagine you have like an app, right, which is trying to do something, let's just say a transaction, financial transaction.
Mm-hmm.
They're using your databases.
Okay.
Some metadata around
mm-hmm.
that.
Mm-hmm.
And there's like a conflict that happens with one of the validators.
Mm-hmm.
And I think what I'm trying to figure out is if you're going to go to Ethereum to resolve the conflict,
Mm-hmm.
you're introducing like a lock time interval, right?
Mm-hmm.
The app now has to get like
Mm-hmm.
handled, right? In some sense, like.
Good. So what's the question?
No, I think the question I'm running was, it seems like you can't really, I think apps will have to be designed in a way where they can't really trust that any particular query they get back from the DB is actually fine.
Yes.
There might be conflict at any point, right?
Yes. So the way there is finality. So after like a few validations, you're like, okay, that's final.
Right.
Yeah. And that was like, but yeah, before that, so basically when the real-time database returns results to the client, these results might not be correct. But that's for this database puts the stake to Ethereum. And basically, if it's found that this node has presented incorrect results, then let's say half of the stake is slashed and half of the stake is given to the client, to compensate. So it's because stakes are not, like for the problems that are like financial problems, the stake should be like really huge. And for the game problems, the stake can be like small enough to just, like pay off like $10 to the player. Mm-hmm. Mm-hmm.
How does it contrast with something like Piccolo, network, or
Mm-hmm.
So as a developer making a choice about a decentralized database, how do you suggest we think about the landscape and how each option fits?
Mm-hmm. Mm-hmm. So I'm not sure, so I heard about Piccolo, but I'm not sure what's their actual design is, and I'm also not sure what their state is in. But I can talk about few other things that I'm aware of. So comparing this to IPFS, a Swarm is easy. IPFS or Swarm, they provide you mostly the key value interface, and this allows you to perform arbitrary queries. So that's like a big difference. But on the other hand, Swarm has a much higher guarantees that the data you store there is correct. Within might sometimes produce, like if the nodes are malicious, it might produce incorrect results. We can also compare it to, let's say, OrbitDB. And what OrbitDB is basically OrbitDB is a kind of thin layer on top of like IPFS. So now you can have more sophisticated data structures. And so here's the thing. If you deal with data structures, so there was like a really cool talk not so long ago that any pointer-based data structure, like if you say, for example, you take a pointer-based data structure and store this data structure in a decentralized storage, like in a decentralized way, and then you query a chunk, like some part of this data structure, it's possible to build a Merkle proof for this data structure, like for the results that you have received. Like let's say, for example, you have you can start with a Merkle tree, so you can store some big chunk of memory in the decentralized node, and then you request like few bytes from this memory, and you can provide this node can provide a Merkle proof that these bytes correspond to the stored data, right? So OrbitDB is kind of built like that, but not for just memory. It allows you to have more rich data structures. But what the trade-off that you have is that you cannot deal with the complex queries. Let's say, for example, if I want to perform an aggregate query over the entire table, the client will probably have to download the entire data and perform the aggregation itself. What else is there? There is VaultDB, and I think these guys, they provide the SQL interface, but I think that's quite base. It's very similar to the key value data source. So it's also it's not also not arbitrary queries. So but I'm not sure if I can talk about Piccolo right now. So I'm not sure what how exactly they are structured. I would love to read the white paper though. Cool. All right, thanks guys. And yes, I'll do the hours.
Hi, everyone. Oh, that's loud. Hi, everyone. I'm Alex. I'm one of the co-founders of Near Protocol. And let's talk about sharding. So a couple words about myself. I was the first employee at a company called MemSQL. It's a distributed database. It's a sharded database, which is relevant when you build sharded blockchains. Before MemSQL, I was at a company called Microsoft. And then after MemSQL, after I left, we started a company with a good friend of mine, Ilya, and that company eventually became Near Protocol. Way before I moved to Silicon Valley, I was doing competitive programming. If you ever heard of ACM ICPC, it's a sort of, it's a championship in who can solve competitive programming problems faster. I did very well there. I got a gold medal in the international championship. And Near Protocol it's a sharded blockchain. It has several people besides myself. There are a couple other guys from MemSQL, so many of us moved from there. A lot of ex-Googlers. Besides sharding, the second biggest emphasis at Near is to build a very usable blockchain, and I will talk about it in a second. And one reason we believe that Near could win the race to the best sharded blockchain is because we have one of the strongest teams with the industry background, right? There are several legendary academic teams, right? You probably can name a few, but very, very few who come from industry backgrounds. Cool. So usability. Before we talk about sharding, I will cover very quickly the problem of usability, right? if you think today about building a very fast blockchain, it is very similar to building a huge stadium in the middle of the desert, right? And when you think of multiple blockchains competing for TPS, it's effectively having two stadiums. One have 100,000 seats, another one has 120,000 seats. And there's like 3 people total who actually want to watch a game, right? And so then those stadiums start competing for those 3 people. So before we start competing for any TPS, which is higher than 100, we actually need to find 100 people who want to use blockchain, right? And so today the number of actual daily active users is very low. And the way we approach that is, our hypothesis is, if you actually make blockchains to be super easy to build for, and then you make applications to be super simple to use, then more and more people will start adopting the blockchain, because the blockchain actually provides quite a bit of value for decentralized finance, but also for Web3, right? The world today is in a disastrous state where the duopoly of Google and Facebook owns all the data you have, right? But you cannot compete with them, because no matter what you build, it's always going to be worse, because you don't have data, right? And so Web3 has a promise. I'm not going to go too deep into that, but Web3 has a promise to fix that. But for as long as you have to go to Coinbase, go through KYC, buy some Ether, install MetaMask just to buy a CryptoKitty, for as long as that is the case, there's 0 chances we will have any meaningful adoption. And so before I will talk about sharding, I will quickly show a demo of development experience on Near. And so if you ever build for Ethereum, hopefully you will see the difference. So our online IDE is located at near.dev. It's a fork of Assembly Studio, of Assembly Script Studio. Assembly Script is a flavor of TypeScript, which in itself is a flavor of JavaScript. And so that means that if you know JavaScript, you can actually start writing right away. You don't need to learn anything new. And so it immediately shows you a few examples. You can just fork and look at them. So I will fork a guest book as a simple toy example. And the guest book, on the left, what you can see is main.ts is the actual smart contract. So smart contract is written in TypeScript, which is, right. And it's very short. Like this is the entire guest book. And it entirely is built around this concept of a collections. So collections is some persistent data structure. And so the vector of posted message is a class defined here. Oops. And so the vector of posted messages is effectively a persistent collection. The collection will persist between invocations of the smart contract. And then adding a message is as simple as just creating a message and actually pushing it to the collection. And then getting messages is as simple as just fetching them from the collection, right? And once you build the smart contract, one thing which we did is, that's more of a sort of, so one thing about Near is that the front end is also part of the contract. And the idea behind that is that today, if you're using IDEX or if you're using Augur, you actually, to begin with, you trust the host that hosts the front end. Right, so in case of Augur, you can download it from IPFS, but in case of many other services you use to then blockchain, you actually hit some front end which is hosted by a centralized entity. That entity at any moment can change that front end, and that when you do some transaction and MetaMask says, would you like to sign it without any extra information, that transaction could actually be transferring all your money to some third-party service, right? And so once you finish building something on Near, in one click of a button, you can actually deploy it on a testnet and immediately invoke it. And that creates a very fast iteration as you build. Right, so you build something, you make some changes, immediately you post it on the blockchain. You don't need any browser plugins. It uses a hosted wallet, and then you're ready to go. Right, so that's sort of the experience we want to see. And so development experience you can already try. And user experience, we're working quite a bit on it, and we're going to be posting some breakthroughs we've made recently on that. So stay tuned. And with that being said, let's actually talk about sharding. So sharding, why do we need sharding? If you use Ethereum today, you know that Ethereum can do 12 transactions per second. It's very slow. And there are solutions which are not sharded, which improve on that. My favorite example is Thunder, who just recently launched. Thunder can do 1,000 transactions per second, or so they claim. And 1,000 is way more than 12. And so Thunder can solve the problem today. But if we all adopt Thunder, the next thing you know is 2 years from now, we're at capacity, We're using 1,000 transactions per second, and then we see new wave of blockchains trying to push it further, and then that will be happening every single time. Sharding is an approach which allows you to get around it. With sharding, there is no limit on the TPS. The TPS grows as the adoption grows. And so effectively, if you build a sharded blockchain, you're not necessarily going to have 1,000 TPS today. You might not need it. You will have maybe 100. But then as adoption grows, it can go to very large numbers, to millions. And so let's see how it actually works. So this is a single blockchain. It's Ethereum. It gives us 12 transactions per second. It's very slow. Let's say we want 36 transactions per second. It's very simple. We just run 3 blockchains. And that's it, scalability solved. There are a few problems with that. Problem number 1, the blockchains actually do not communicate. And so if my account is on one blockchain and my friend's account is on another blockchain, it's actually very hard for me to pay them. But there's an even bigger problem. And the bigger problem is that how do we ensure the security of multiple blockchains? If you have just one blockchain, and there is some sort of people who are willing to spend their resources on validating the blockchain, you need to corrupt 51% of them, right? If you have multiple blockchains, and each blockchain is, those validators split, right? We presume there is some resource that they have to split between the blockchains, right? So if it's proof of work, you cannot mine on all of them. You can mine only on one of them. If it's proof of stake, you only have limited amount of money. You will stake only on some of them. And now for you to break any of those blockchains, just one, if you want to break, to break just one of them, it's significantly cheaper. So if there's 10 of them, you're actually only spending 5% of the total security of the system to corrupt it, right? And that's exactly what happened recently with ETC, right? ETC would be one of those blockchains which has significantly fewer security than the total security blockchains have. And so there's a common solution to that, which is it says, well, let's not allow people to choose which blockchain to verify. Let's assign them randomly. Right, so let's say there is a total of 1,000 people who are willing to validate, or like hash power, and you control 10% of that. If you can choose where 10% goes, you can send it to ETC and you can corrupt it, right? That's what you do. You go to NiceHash, you run 10% of hash power, you corrupt ETC. Now imagine that actually when you have some hash power, your hash power is randomly assigned to one of the chains, of the existing chains. Then what happens is if you control 10% of hash power, you will end up having 10% of hash power on every blockchain, or like around that. There's some variance, of course. But in reality, you will not be able to corrupt any of them, even if there's 100 of them. And that solution works. That's a working design to sharding security if we assume that 30% or less validators, or 50, depends on your security model, some threshold of validators are not corruptible, meaning that we cannot, meaning that we have to, if we control 10% of the hash power, we cannot later corrupt hash power after we know where it went, right? But in reality, this is a very unreasonable assumption, because if you think why people mine, or why people stake, or why people validate, majority of them actually do that because they want to make more money, right? Nobody runs a huge mining rig for Bitcoin because they just want to create more security for Bitcoin. They want to make money. And majority of them actually immediately sell Bitcoin as they mine. And so, but if we assume that they're not corruptible, that is, the system is completely secure, right? So let's say we're using some sort of BFT consensus, such that if 2/3 of people signed on the block, we know that that block is irreversible unless more than 1/3 of them collude, and we presume that there is less than 30% malicious corruptible actors. And then think about, so that little character on the very left, let's say this is you, and you want to know the latest block. You go to the current validator set, to the people who presently validate the blockchain, and you ask them, what is the latest block? And they give you some block, and 2/3 of them sign on it. You know that last block must be correct, because you know that at least more than 2/3 are honest. How did they know? How did they learn about the previous block on top of which they built the last block? Well, they did the same thing. They went to the validators from the previous epoch, and they asked them for the last block. And by the same reasoning, that block was valid. And by induction, you go all the way back to the Genesis block, which is valid by definition. And so you know that the entire chain is valid without downloading it or validating it, just by looking at the latest block. Unfortunately, we cannot assume that less than 30% are corruptible. What we can assume is that less than 30% are malicious. That's a more reasonable assumption. But you assume that of the remaining actors, actually a pretty large percentage can be corrupted adaptively, meaning that once it is known who is validating what, it is possible to find those people and to offer them more money than what they would lose if they collude, right? And so let's say we have 1,000 shards. And so that means that every particular shard has only 1,000th of the total security, and that's how much we would have to pay to corrupt them if we can find them. What we can do? Well, one thing we can do is we can create a fork. We can create a double spend. And there's a very well-known solution to that. Let's say Ethereum exists, right? So Ethereum 1.0 exists, or Bitcoin exists. Then as you build those short chains, so you have 1,000 chains, so let's say there are 2 of them here. When you create block B, what you do is you snapshot the header of block B onto Bitcoin. And Bitcoin has very high security, right? And what you effectively can tell later is that if there is some block, let's say block B, which is on the snapshotted to the Bitcoin, then that block is canonical no matter what. So no block which conflicts with it can ever become canonical. Then double spend becomes insanely expensive. Even if you can build a longer chain, like let's say you can fork out just before B and build a significantly longer chain, nobody will respect it because they will say, well, your blockchain is not built on top of the latest block, which was snapshotted to Bitcoin. And effectively use security of Bitcoin, which is very high, to prevent forks on all the shards, right? And if you can prevent forks, you can prevent double spends. But if you corrupt the entire shard, you're not going to create a double spend. You will create something significantly more disastrous. You will create a thing that is called an invalid state transition. The idea behind the invalid state transition is that because there's 1,000 shards, it is absolutely infeasible for any entity to validate all of them, or at least you would not expect majority of entities to validate all of them. And so what you can do is you can corrupt shard 1, and you can create a block which is completely invalid. It's a block which before the transactions were applied, let's say I had 0 tokens, and after transactions were applied, I have 1 million tokens, but not a single transaction sent me money. Right, so it's a block which is just straight up invalid. If you validate it, you will say, well, this block is invalid because someone has invalid number of tokens. But hypothetical users of shard 2, they don't validate shard 1, they don't know about it. And so then validators of shard 1, which are corrupted, they will create another block C, which is perfectly valid otherwise, besides the fact that it is built on top of an invalid block, and they will create some sort of cross-shard transaction. They will send money. And you need to support cross-shard transactions if you want your blockchains to be usable. At this point, as of block Y, completely invalidly minted tokens now belong to someone on a perfectly valid chain, right? So that's invalid state transition problem. There are multiple solutions to that. The most simple solution is called fisherman. The idea of the fisherman is, well, I guess the most simple solution is to pretend the problem does not exist, right? But if we say it does exist, then fisherman would be one of the best solutions. The idea of fisherman is, let's say there's at least one validator who is not corrupted. Or maybe all the validators are corrupted, but let's say there's at least one user of the blockchain. There's someone who's running a full node, who's validating the chain, and they see that the block B is incorrect. What they can do is the moment they see that block B is incorrect, they can prepare some small proof that the block is invalid, and they can send it to any other shard or to some centralized chain, and they can claim some reward for that. Right? And so effectively now, the shard 2, as they receive the cross-shard transaction, they will have some challenge period during which they will wait for someone to actually speak up and say, you know, actually there was an invalid block. You should not respect the cross-shard transaction. The problem with fishermen is that the cross-shard transactions become extremely slow, in the sense that before the fisherman, if you think how much it takes for a cross-shard transaction, if we use BFT consensus, block C is created. It has a 2/3 + 1 signatures from the validators. The moment cross-shard transaction is received on block Y, if they believe that those validators are not corrupted, they can immediately apply the state. So the cross-shard transaction time is 1 block. It's very fast. With fishermen, you need the challenge period to be very long, because you need enough time for the fisherman to recognize that the invalid block was produced, to identify it, download it, validate it, find the invalid transaction, prepare the proof, send it. Right? So you want at least like 10x the delay. Right? And so your cross-shard transactions become 10x the block time. So if the block time is 6 seconds or 12 seconds, it becomes 1 to 2 minutes, which is relatively slow. Another approach to fishermen would be to say, well, instead of doing that, what we're going to do is we're going to say, so let's say that first red block in shard 1 is the first invalid block. As we build a blockchain and we create a 1 and we initiate the cross-shard transaction, the second chain, the second shard will immediately apply the state. And when fisherman, if fisherman at any point fishes, shard 2 will also fork out. Does that make sense? So effectively we're saying if the block received an invalid state transition from if a block applied something, some transaction which originated from an invalid block, the recipient block is also invalid. And so because of that, that will invalidate block A2 the moment the phishing attempt happened, and then the second shard will also fork out. And so what happens, that gives you atomicity effectively. That means that it will never be the case that the source transaction did not happen, but the destination happened, right? So with this, the cross-shard transaction is now very fast. It's again one block, but your finality is pretty bad. Because on the second shard, you might be running a full node and you're validating every block, and you're pretty certain that all the blocks are correct, but then suddenly someone phishes and your entire chain rolls back, right? But probably you're not going to allow arbitrary rollbacks. Probably there's going to be some delay, but still, the finality is pretty bad. But it works way better if, let's say, you're an exchange and you're running shard 2 and you're also running shard 1. Then if the cross-shard transaction happened, if you know that shard 1 was valid, you know that phishing attempt will never happen. So for you, finality is instantaneous. So finality is instantaneous for those who are willing to spend more resources validating. Okay. So now, how does the fisherman actually create a proof, right? How do you create a small proof that the block was invalid? So let's think about the problem here. Let's say there are Alice and Bob are validating shard 1, and Charlie and Dave validating shard 2. When you validate a shard, you need the state of the shard, right? You effectively need to download the full state of the shard. Let's say it's 100 gigabytes, and then you're applying blocks. And so when shard 1 had an invalid block, right, Alice, Bob, and the fisherman guy, they all have the state. They can easily apply the block. But Charlie and Dave, they do not have the state. So for them, it is impossible, even when fisherman says the block is invalid, and Charlie and Dave downloaded the block, they cannot validate it because they don't have the state to apply the transactions. And the common solution to that is to use so-called Merkle proofs. The idea of the Merkle proof is that the state, let's say the state is 100 gigabytes, that would be the lower level in this picture. And what you do is, you're creating a tree where every node is a hash, or it's a binary tree, and every node contains a hash, which is pre-image resistant, of the two children, right? So if this, like let's say this is a count of some person and this is a count of some person, and they have balances and their public keys, that would be the hash of their balances and public keys. And this would be the hash of this account, and this will be the hash of these two hashes, right? And then at the very top you have one node that's called a Merkle root, and the Merkle root goes to the blockchain. So the Merkle root is in the header of the block, and everybody knows the Merkle root of the full state. What happens next is that if you want to prove, like let's say there is a transaction which changes this account, and what you want to prove is you want to say, oh, you know what, that account had 5 tokens before, transaction gave him 5 more, and now he has 100, so you want to prove it's invalid. You don't need the destination, the person to whom you're sending a proof to have the full state. Instead, you're saying them, this account had 5 tokens, and I can prove you that because you know the Merkle root at that state. And what I'm going to give you is I'm going to give you this second account, so you will be able to compute this hash. Then I will give you this hash. That will be enough for you to compute this hash, and I will give you that hash to compute that hash. And if you imagine this tree being taller, the number of hashes you need to provide is logarithmic in the size of the state, right? So in Ethereum, that would be something on the order of like 40 hashes or 48 hashes, which is way smaller than the full state, right? And so because of that, you can actually create a very small proof of invalid state transition. You just say, this is the Merkle proof before transaction, this is after transaction, and this is the transaction, and you can see it's wrong. Now, there's a problem. Imagine we're in a shard 1, so this is shard 1, and this is the validators of shard 1, and we corrupted them. Because we corrupted them, they can create a block, they compute the header of the block, they sign on it, their signatures are sufficient for the block to become valid. We have more than 2/3 plus 1 of them. Then they send the header of the block to you. You're a light client. So you might be a user of the blockchain, or you might be a validator of a different shard, or you might be a fisherman. But the thing is, they actually don't have to send you the block, right? They already send you the header. You already confirmed that the block is valid. So the second shard might have received that header and some information about the cross-shard transaction and apply it. The problem is that the fisherman, to create a proof, obviously needs to see the block. They need to see the transactions that happened. But if the block is not distributed, they cannot do that, right? And so that's called the data availability problem. And it's a significantly bigger problem, the state validity problem, than state validity problem, because you can prove that state is invalid cryptographically. But obviously, you cannot prove cryptographically that something is unavailable on the internet. Like, you cannot come to me and say some file is unavailable on the internet because because I cannot distinguish between the file actually being unavailable and you pretending you were not able to download it. Does that make sense? Right? Or it could be that you actually couldn't download it, but then by the time you come to me and say it's unavailable, it became available. Right? And so I try to download it and like, no, it is there, you know? Okay, so how can we solve data availability? One way to do that is we will not try to prove that data is unavailable, but we will only take some action once we're sufficiently convinced it is available, right? Because data availability is easier to prove. Data is available if you actually manage to fetch it, right? So here's first simple idea. Let's say there's a block. We're going to split it into 100 parts, and we're going to send one part to 100 different people. And then for me to convince myself the block is available, I will try to fetch 5 of them. It's still significantly less than the full block. And if I manage to fetch 5 of them, I will say, well, there's a decent chance that they're all available. That is obviously wrong, because I will distribute, the malicious actor will distribute 99 of them instead of 100, so 1 will be unavailable. And then there's a very high chance that if I sample 5, all 5 will be available. But the block is still unavailable, right? And so there's a solution to this problem, which is we use erasure codes. So what we do is we start with the block. So let's say these 4 parts is the block, split into 4 equal chunks. And then we compute so-called erasure code, which is a construction which creates more chunks such that if you have any 4 of them, you can reconstruct the block, right? So there's 8 total, any 4 is sufficient. That means if you manage to sample 2, there's a very high chance that the data is available. Because every single, well, that's a bad example. Let's say there's 100 total, 200 with erasure code, and you sampled 5, right? You have 1 in a 32 chance at this point for data to be unavailable. Because every single time you sampled 1 part, you had 50% chance to get to the unavailable data. Does that make sense? Not quite. Okay, so let's say that this is 100 chunks and this is 100 chunks. And any 100 of those 200 is sufficient to reconstruct, right? For data to be unavailable, more than 100, so 101 need to be unavailable. And so if you sample 5, every time you sample, you have 50% chance to get an unavailable block. So if you sample 5 times and all 5 times you actually fetch something, there's 31 over 32 chance that the block is available and only 1 in 32 that it is not, right? But even that, like that's a building block, but getting from here to some construction in which you can actually prove data is available is very hard. There's a paper by Mustafa from Chainspace called Fraud Proofs. That paper was very famous because of another co-author on the paper, and that's effectively the approach that is used by Ethereum today. Right. So okay, so before this talk started, you might have heard of sharding, you might have had some questions, and so far we created more questions instead of answering some of them, right? So up until now, we still don't know what to do with state validity under adaptive adversary. We have no idea how to reach finality with fishermen, and we didn't figure out how to make accountability for data availability, right? So far, we didn't get any closer to building working sharding. And so this is where a concept of whale fishing comes. So whale fishing is the new design for sharding that we published 1 week ago on its research. We haven't committed yet to building it. So far, we're building prototypes and figuring out if that's actually better than existing sharding designs. The goal of whale fishing is actually to have sharding where under adaptive adversary, the probability of state validity of invalid state transition is very low, right? Which on itself, to achieve that, you need to solve data availability to some extent. So how does it work? First of all, instead of modeling sharding as multiple shard chains, we model it as a single blockchain where the blocks are huge, right? So let's say you have 100 shards, then you will be producing blocks, let's say every 15 seconds, and every 15 seconds the block will contain all the transactions for all the shards, but they will be organized in a way that at the beginning you will have transactions for the first shard, then for the second shard, etc. And the idea is that nobody will ever observe the full block. People will only observe those parts of the block. And nobody produces the full block. Instead, you have some number of so-called block producers, or whales, because block producers are going to be someone who's taken a lot of money. And for simplicity, let's say there are as many shards as there are block producers. So let's say there's 100 shards and 100 block producers. And we're going to assign 4 block producers to every 4 shards. For example, the first 4 shards, and this is shards, the first 4 shards will have the first 4 block producers The next 4 shards will have the next 4 block producers, etc. And they just take turn producing that particular chunk of the block at every given moment. For example, this is block 1 on the left. And so the blue guy produced the first chunk, the yellow guy produced the second, etc. And on the second block, you can see the blue guy produced the second chunk, the yellow guy produced third, etc. And then they rotate. Like after the blue guy produced the fourth, he goes back to produce the first, right? In a more simpler approach, you would actually just assign 1 block producer per shard. But in this case, if one of them is offline, 1 shard will completely stall. That would not be good. While if you have 4 of them, you need 4 of them to go offline for the shard to stall. And if that's also too likely, you can increase the constant. You can say, well, there's 10 shards per 10 block producers. And so one thing that happens is that once a block producer, have a question?
Yes. Can you go back to the previous slide? Traditionally, in a block, you have one miner who groups together all the transactions, computes the Merkle root, and then commits that to the block there. If you have 6 different people, how do they all get together and agree on what the block looks like and what the Merkle root looks like?
Right, so the question is, in a traditional blockchain, it's usually 1 block producer, block proposer. They propose a block and everybody, and they compute the whole block. So here, because nobody ever sees the full block, nobody also can propose the full block. So the idea, which I don't have a slide on it. I was sort of planning to omit it. But the idea is that the full protocol is that each of them produces their proposal for their shard, and then they start a protocol in which they're trying to figure out who of them, like each of them says which proposals they saw, and for a few iterations they will try to figure out some large set of the proposals. Like ideally, it's in their interest to have all the proposals. Like if the block has all the shards, all the chunks, everybody's reward is maximized. The reward is proportional.
So this is all just for each node will commit like a subblock and then maybe
Yes.
someone else will group that into a neighbor block.
Yes. But even that full block will not technically exist. But yes, so they will compute a global header. So once they agree, so they use some consensus, let's say Tendermint. So they use Tendermint to agree on some set of them such that, so effectively they want to find this clique in a bipartite graph where on the left you have validators and on the right, block producers. On the right you have shards. And each of them said which shards they saw. You want some clique. You want some set of block producers and some set of shards such that each of them said that they saw that subset of shards. Right? And the clique in the bipartite graph is it has a polynomial solution, right? So you can actually do that. And after that, once they reached an agreement, they all agreed on what exactly the block is going to be. Each of them can independently compute the global Merkle state root hash, and they can compute all the remaining header information. Cool. So how do they actually know if they cannot exchange the blocks? It is infeasible for all of them to send blocks to each other. If there's 1,000 shards, that would mean that at every timestamp they will have to download the 1,000 blocks. So instead what we do is, so that circle is one block producer who produced a block. And let's say there is a total of 7 block producers. So the block producer will compute an erasure code on the block such that, and that erasure code will have 7 parts such that any 2 of them are sufficient to reconstruct the block. Right, but if there is, let's say, if there was 100 validators, the erasure code will be such that any 34 are sufficient. So effectively, any 33, 1/3 minus 1. 1/3 minus 1 is sufficient to reconstruct. And then they send 1 part to every block producer, and the block producer would only say that only commit to signing a block with a particular chunk if they receive their part, the erasure coded part of that chunk. And so what that means is that if 2/3 of people signed, even if 1/3 of them is malicious, the remaining third is honest. And so you have sufficient number of honest people to reconstruct the block. Does that make sense? And so effectively, if there's a signature on a block with some number of chunks, every single block producer attested to the fact that they have 1 part of erasure-coded chunk. And for as long as 1/3 of them is honest, of those who signed, you can reconstruct each and every one of those chunks because information that 1/3 possesses is sufficient to reconstruct it. Cool. So now let's say, but there's only 4 block producers, right? It is very easy to adaptively corrupt them. So what do we do with that? The idea is that there's another role called fishermen. And so fishermen, they're fishing whales, and hence the name whale fishing. And what happens is everything happens in epochs. You can think of an epoch as some long period of time, let's say 1 day or 7 days, during which block producers and fishermen do not change. Right? And then the epoch ends and they somehow reshuffle. But within that period, they do not change. At the beginning of the epoch, a particular fisherman, they roll a die, and they get some bit mask of shards they're going to be validating. And let's say that bit mask will always have exactly 4 ones. On my example, I have 2 ones. So there's 7 shards, and they had ones at position 3 and 7 and 6. And so for the duration of the epoch, they will be validating shards 3 and 6, and they will completely ignore the remaining shards. And so what happens is every time the block is produced, the fisherman will validate shard 3, and the fisherman will validate shard 6, but then they will sign the entire block. Why is that important is that nobody knows which fisherman is fishing for which shards. Because the property of the random function, it's called VRF that we used, is that only the fisherman knows the outcome, and nobody else can know the outcome until fisherman reveals it. And the fisherman cannot reveal something that was not the output. Does that make sense? So effectively, the fisherman cannot lie later that they had some different outcome. And so because of that, because they sign on the entire block, they're not signing just on the shards, nobody knows which blocks the fisherman, which shards the fisherman is validating. And so if you have, let's say you have 1,000 fishermen and they're signing every block, you know that every fisherman is validating 4 shards. So every shard has like quite a few, let's say there's 100 shards, so each shard has 40 fishermen, but you don't know who they are. You don't know whom to corrupt, right? And the way phishing works is that, so let's say full block 1 was produced, and the fisherman, a particular fisherman, validated their shards. They have 10 blocks to do that, because it takes time to validate, right? So if block is produced, you need to download the block, you need to validate the shards, you need to reconstruct it if it's poorly available. So we give them some time. Let's say we give them 10 blocks to do that. So within 10 blocks, they need to commit to either yay, meaning that everything is good, or to nay, meaning that actually something is invalid. They're committing, they're not revealing it yet. And then they have 10 more blocks to actually reveal what they committed to 10 blocks ago. And why we need it is going to become evident in a second. So effectively what happens is block 1 was produced. By block 10, the particular fisherman will commit to yay or nay. Let's say it's yay. And by the block 20, they will reveal what was committed for block 1, and they will already commit something else for block 10. Does that make sense? So why we need it is that, let's say block 1 was invalid, and then by block 7, there are 2 fishermen. Fisherman 1, who was either lazy, and they were just not validating blocks, they were trying to collect free money. They committed to yay. And fisherman 2, who was actually doing their job properly, they committed to nay. So what happens is that by block 13, when fisherman 2 reveals nay, for fisherman 1 it's too late to pretend they also knew that the block was invalid. So that commit reveal is necessary so that fisherman cannot try to not do the job. So if commit reveal did not exist, and fisherman 2 just said, the block is invalid, then the first fisherman can say, oh, you know what, actually someone said block is invalid, I will just copycat their challenge, right? With commit reveal, by the time the actual phishing is revealed, if some fisherman was slacking or was intentionally malicious, it's too late for them to pretend that they actually did their job right, because they committed to yay. So at this point, they have 2 choices. One choice is not to reveal at all, which is slashable, or to reveal yay, which is also slashable. So they will get slashed no matter what. But here's the problem. When the fisherman says nay, we actually don't know whom to slash, because some fishermen signed on the block because they didn't validate the shard at all. They were not assigned to it. So what happens is that if someone says nay, at that moment, every fisherman has to reveal their bit mask. Right? And so if you're revealing your bit mask and it has 0, you're good. Nothing bad happens to you. If you reveal the bit mask and you have 1, then we'll look at your verdict. If it was yay, you get slashed. If it was nay, it's good. And if you don't reveal your bit mask, you get slashed because it is presumed that you're not revealing it because you're malicious.
What problem are we solving with this commitment?
So if the commitment didn't exist, then like let's say they did not commit, but they immediately said yay or nay, the lazy fishermen could adopt a strategy where they wait for other fishermen to fish, and if nobody fished, they will commit to yay. So they're not even malicious, they're just lazy. They don't want to download the state, right? And they say, I'm going to be committing to yay unless I actually see someone else, not committing, I'm going to be saying yay until I see someone else saying nay. Does that make sense? And then you will converge, then there's a Nash equilibrium where every fisherman is lazy, and they all just say yay, and your security is 0, and you're just paying a lot of fishermen in vain. But with commit reveal, you already committed to your outcome.
So then at what
Yes. And they all get slashed, yes. A lot of money get lost. That's actually very good. Yes, that's what happens, and that actually increases security even further, because imagine you managed to identify those fishermen. So effectively, let's say you went there and you said, prove to me that you're validating the shard. Like, send me your bitmask. You can prove to me the bitmask is such. I want to corrupt shard 7. If you send me the bitmask with the proof that you're validating shard 7, I will pay your stake multiplied by 2. For any fisherman, that seems like that's money, right? You're going to lose your stake, but you're going to get twice the stake. So that's good. But here's the thing. Imagine you're the last fisherman who is not corrupted yet. You know that 5 of them are corrupted. So by the time the malicious behavior is happening, they will all get slashed. And if that's you who's fishing them, you're getting 5x the stake. So at that point, it's actually more meaningful for you to fish than to get corrupted.
So is it if you call someone out, but you're wrong, lose all your money?
You lose your stake, yes. But you would only call someone out if you have a cryptographic proof they're wrong. Right, you use the same verifier function as everybody else, so you will know if your call is correct beforehand. Right, and so corruption now is quadratic in cost. So if there's 40 fishermen, you need to pay 1600x the stake, which is great. But also, you need to broadcast your intent to corrupt, because you cannot target people. You need to broadcast the intent. And so every single fisherman knows you're about to corrupt the shard, which is very good for the system, right? Cool. So that's the overview of the whale fishing. So a few words about other interesting projects Near is doing. So one interesting project is called Whiteboard Series. If you never saw Whiteboard Series, you should check them out. The link is near.ai/WBS. Stands for Whiteboard Series. It's a series of videos where we invite other protocols to our office, and we talk for 1 hour in front of the whiteboard exclusively about their tech and nothing else. Right? And so we have episodes with Cosmos, Polkadot, Ethereum, Maker, multiple Plasma episodes, Ontology, Quark Chain, and many more. Yeah. Then if you want to try out Near, if you like the demo at the beginning, it's near.dev. That's the studio. And docs.near protocol is documentation. Finally, we optimize a lot for vanity metrics. So please follow us on Twitter @nearprotocol. Thank you. Let's see if it works.
Let me get it. No. Mine. No. I just got it out of my bag. Oh. Well, we can try that one. It's not like Max, does it?
who doesn't like it, do you mind emailing?
I mean, I was just going to show a bunch of websites, so if we have a laptop that works, I can probably just. Yeah. Cool.
The actual 21st century operating system. Let's try it.
That's so weird. I've never.
Works for me.
Yeah, it works on your computer, so it's all good.
Cool.
All right, sweet. Hello. So I guess the way I've been doing these is just kind of a brief tour of the Cosmos network post-launch. Just give me a second to bring some stuff up. Sweet. All right. So, okay. So, who knows that Cosmos launched? Most people know. Cool. Yeah. So, probably the last year of my life has been mostly my job has been to make sure that event happened, and so I'm super glad that it did. The Cosmos blockchain. Okay, well let's just like walk through some stuff. Okay, so Cosmos blockchain is 3,676.50 blocks tall. We have 103 validators, though I think we have like 1, 2, 3, 4, 5, 6, 7, 8, 9 are offline. So, 90-something validators. The network at the moment supports up to 100 validators. Things that the Cosmos network was notable for is we are the first decentralized launch of a BFT blockchain. We are the first BFT blockchain where the majority of the nodes are not run by either the project themselves or a foundation or something like that. In fact, Tendermint and the Interchain Foundation run no nodes on this network. Some nodes are run by employees, but on their own. Other things I'm really happy about, of the top validators, Bitfish, which is the proof of stake operation by our friends at F2 Pool, Certus One, and Figment are all not participants in either the fundraiser that we had back in April or the project. They got to this to the top of the validator set based on being awesome, building reputation through testnets, doing really well in Game of Stakes, and all in all, I think that's like a huge win for the project, for open source, for building open entry systems, etc. Things that are noteworthy about the state of the network right now are, so, we're running Tendermint, with 90-something validators. This is all dynamically assigned. We're at about, every block explorer, there's like about 6 block explorers for Cosmos right now. And everyone kind of shows different things. So where we are right now is we have about 50% of the network is bonded, which is pretty good. I'm pretty happy with. And so that's the state of things. We make a block every roughly 6.8 seconds. Also nice, nowhere near as fast as we could be going, but the blocks are mostly empty. What is the primary thing that's going on in the network right now is we are deciding to enable transfers. So for reasons that had a lot to do with security, the blockchain network was launched without the ability to transfer atoms from one account to another. The reason why we did this is we did a fully decentralized launch of a network, and we had no idea how the security of the network would turn out. It all turned out fine, but there were brief periods of time where, for instance, my validator controlled a third of the network. Not super great, but all of those things have evened out, and we are going to do an upgrade of the network probably sometime like next week. So that's kind of like what we're looking at. So we have these governance proposals. The first governance proposal passed. It was basically increase inflation by 20%. So that usually seems to be broadly popular. We're running this sort of liquid democracy system where any delegated atom can vote. Validators vote with their delegates, but then if their delegates vote on their own, it overrides the validator's choice. So pretty good voter turnout. 97 mil, 100 million-ish atoms voted. So interestingly enough, the first proposal to enable transfers failed, or will imminently fail, mostly over process issues. People got super upset, and we burned 501 of my atoms. So, and then we have transfers enablement number 2. Seems to be passing. Some people are against it, mostly over process issues as well, including a number of people who work at Tendermint. So things are going well, and network seems to be humming along. I'm super happy that we got through multiple weeks without the network halting. Feeling really good about that. Let's see what else is going on. So we have this one blockchain. It seems to be doing great, but we were supposed to build a network of blockchains. So how's that going? So let me just ecosystem. So the network of blockchains seems to be going pretty well. We have the Iris network, another very similar blockchain to the Cosmos Hub, sort of a China-focused sister network to the Cosmos Hub, is live. People are transferring Iris tokens on it. Seems to be going great. The Binance chain, this is the UI for it. So the little trading bars don't seem to be rendering. Not super sure what's going on. But when it sort of works better, it still hasn't launched yet. Maybe this, oh, there we go. So they have this test net. It actually looks like a centralized cryptocurrency exchange, except it's running with an online order book on top of a blockchain. Seems to be going great. Mainnet sometime later this month. We have another blockchain called Lino. They do have an explorer. I forgot how to get to it. Let's see. Finance Testnet Explorer. thing. Testnet.binance.org. Here we go. So they've done about 832,000 transactions on this testnet, though I'm not exactly sure how long it's been running. 700 blocks, 1 second blocks, like about a week. So then there is this another blockchain called Lino, and Lino powers this website called, this app called DLive. DLive is another Cosmos-powered blockchain. It's sort of like Twitch, but where tipping and everything is on-chain. And they have done 11 million transactions on this blockchain. So pretty good. So all this stuff is like early signs that this whole system is working. You know, we have a live blockchain that's probably the most decentralized BFT system that's ever been run. We have several more centralized testnets with large numbers of users. We have other folks who are using Tendermint, like our friends at Fluence or friends at Loom, doing really well. So it's great. Everything is going great. So what's next for Cosmos? We are continuing to build open source software improvements to the Cosmos network, to like the Cosmos SDK and the Tendermint software package. The big thing, Cosmos, GitHub. No, that's not what I wanted. There we go. No. Oh, here we go. Yep. Not used Ubuntu in a while. How do I get my presentation? Oh, here we go. Sweet. So the next big thing that we're doing is IBC. So IBC is a mechanism of relaying data packets between chain A and chain B. We're holding public public design sessions on it every 2 weeks. We put them on YouTube afterwards. We're working on them in a repository called github.com/cosmos/ICS. I can show you. Cosmos/ICS. So the sort of open issues are a good overview of everything that we're working on the IBC front. But the problem that IBC is intended to solve is basically this mechanism of moving data packets between chain A and chain B, where chain A and chain B are both to a degree suspicious of each other. So what we are trying to achieve is a form of authenticated messaging that is friendly to blockchains, where the messages are generated by blockchains and consumed by blockchains. And the system is based on light client verification, and Tendermint has a very efficient light client system. So this is what we're working on now. it's sort of designed to, the basic inspiration of IBC was, you know, long before Alex was even in this space, I was thinking about sharding and the data availability problem and adaptive corruption problems. They're all super hard problems to solve. And so what I realized was that there was prior art in the blockchain space or in the smart contract space about how to send messages between blockchains where there wasn't one giant integrated state machine, where blockchains could interact without necessarily believing that that invalid state transitions were impossible. So the entire purpose of Cosmos is to having first built a BFT consensus algorithm, then built a proof of stake mechanism around it, then launched a BFT proof of stake blockchain to now enable this security model where you burn assets on chain A, you get T vouchers on chain B, and you burn T vouchers on chain A, and you redeem T on. This is the mechanism that we do it, where state machine A and state machine B are sending these messages back and forth to each other. These systems will be arbitrarily corrupted at scale and are expected to send corrupted messages. And we use a namespacing-based approach to ensure that users are able to identify what corrupted blockchains they might have exposure to. So that's the sort of focus of Cosmos right now. Are there questions about Cosmos, the Cosmos launch? What confuses you about where we are in this many-year cycle of building scalable blockchains?
What do you see as the first wave of applications that you think will get to for monitoring Cosmos? You know, with Ethereum, we saw that was essentially doing token sale, and maybe now it's a little bit of decentralized finance.
It's going to be a mix of sort of, I mean, like the two examples that I showed you, Lino and Binance, are great examples of what we see as the basic trends. We're seeing a mix of partially, semi-centralized, partially centralized, consumer-facing, high-throughput applications. And what people are doing is they are trying to open source either a monetary, like they're decentralizing either like a money-like layer or a data layer or sort of like a crypto economic game layer of their system to like add that on top of traditional like mobile software as a service applications. And we're seeing DeFi. So those will be, I think, the long-term trends for at least the next year of Cosmos is more of both. There are applications in the DeFi space, and there are applications in the sort of consumer-friendly BFT layer blockchain applications, both coming down the pike.
So will Cosmos enable cross-chain communication between like contracts? So let's say I have like a ERC20 on Near and an ERC20 on Ethereum. Is there a way to set up like an exchange via Cosmos?
Okay, so super interesting question. So the simple answer to the question is, so arbitrary cross-chain contract calls require you to solve all of the sharding problems. You have to solve data availability, you have to solve invalid state transitions, you have to solve consensus correctness across all of these chains. And if anything goes wrong, everything goes wrong. Like the whole system fails in an arbitrary way. But what the cool thing about, or if we go back to, slightly after dinosaurs ruled the earth, the 1990s, these people who are now work at a company who are now the founders of a company called Agoric, had this website that looks like the most 90s thing ever, erights.org. Like literally the most 90s website ever. Okay? And here's what the cool thing about what they show is. These are like the first smart contracts. This is like smart contracts before blockchains. Is if instead of just saying, oh, here's some arbitrary state, our whole system is based on we send arbitrary state between blockchains, what if we actually had a level of formalism above this? The formalism is we have some notion of an object, and there are rules about who gets to mutate the object and how the objects change over time as they're moving back and forth between blockchains. And all of the honest chains agree to follow those rules. In that setting, mutually untrusting blockchains, blockchains that don't have the same validator set, blockchains that where the other blockchain could arbitrarily fail, or like general computers that have these properties, can actually interact with these systems. And so you can have programs and state machines running on one blockchain that get messages according to the IBC protocol, and then are able to like instantiate tokens on another chain. You're able to send a token on chain A to chain B. You're able to send call options on the right to invoke a function on a smart contract across chains. So there are a bunch of things that are going to be laid out in the IBC higher level protocols that define ways in which arbitrary computers can interact over the Cosmos system while maintaining this security model of the blockchains are mutually suspicious of each other.
But that would require overhaul of all the consensus mechanisms currently used.
So the point of Cosmos calls itself the Internet of blockchains. We mostly aren't about what we are trying to. So the entire purpose of Cosmos is, and sometimes it's like worth like coming back to why did we do this? So at least for me, and I started working on Cosmos and like pretty much right after Jay and Ethan showed me the idea, like April 2016. So it's like been 3 years. Okay, so like why was this worth doing? I always assumed that people like Alex who've like built like real high performance systems in their careers, and I'm not a database person and I'm not really a distributed systems person. I just sort of learned these things like by chaining blocks. Would show up and like show us how to like solve these hard problems about data availability and fraud proofs and all of these things. Like it'll happen. The point of Cosmos was I assume this will happen. I want to build a system in which we can have economic integration without political integration. And this is the like wonderful thing about the internet that we have today, which is there are people run servers all over the world. They operate under different legal and regulatory regimes, but they're all able to interact with each other over TCP/IP. The problem with the blockchains that we have today are that to economically integrate, whether it is on Ethereum or Zilliqa or Polkadot, etc., you have to politically integrate. There's one shared set of governance norms. Everybody who holds tokens on Ethereum has to care about every Ethereum hard fork. It's just like extremely complicated and noisy, and you have to bring tens of thousands, hundreds of thousands, and eventually 10 billions of stakeholders together in agreement. The whole point of Cosmos was to get to the minimum viable set of features that we need to re-architect blockchains to allow for economic integration without political integration. That's the whole goal. So then, people who would rather implement their applications on top of Near can implement their applications on top of Near. People who want to implement their applications on top of Ethereum 2.0 can implement their applications on top of Ethereum 2.0. And economic value can be exchanged between these things, making the total economy bigger. And we basically recreate what we did as humans when we created nation states and allowed for specialization and like produced 500 years of economic growth. So that's what we're trying to do to blockchains. We're basically trying to say, the point was not to we have these things called peg zones, which are an important part of the story. We're investing quite a bit of energy and time and money in getting the first peg zones up and running. There's just so much to do there. But ultimately the point, Cosmos will be successful if we end up with a world of blockchains in which the blockchains are exchanging value between each other. They're able to grow their economy. When somebody wants to launch a new blockchain, a new protocol, they don't have to first invent money. That will be the success criteria for Cosmos.
So that last part you just mentioned about inventing money, it seems like there's a huge incentive, especially for new projects, to do just that, so that they have some level of value capture. So what would be an alternative to inventing your own money in that situation?
I could probably find the tweet. But so far I've got a tweet. I'll probably turn this into a white paper over the course of the year. It's what's the alternative to inventing? Well, inventing money is one of the options, of how do you capture value and secure your blockchain. The more likely thing is I think blockchains will end up generating most of their value based on the assets under management. So if people are holding things of value where your blockchain is the ledger, the validator set, the token holders will be able to collect rent on that we'll be able to collect rent on that economic value, and that'll be the primary driving factor. But to get there, we actually have to move a significant fraction of the real global economy onto blockchains. And I would argue that that was impossible, but now Cosmos launched, so it is possible. Cosmos chains are secure enough, high throughput enough, to support a meaningful fraction of the world's economic activity.
Okay, so you just feel like it's tokenizing real estate, securities, whatever.
It doesn't have to be real world. Shelling points, game theoretic mechanisms are all alternatives to corporations, et cetera, are all also viable possibilities. I don't think you have to go out and tokenizing real estate is the be all and end all. Cool. I'll give you the last one. Yeah. So what's going really well, so we have this thing called the Cosmos SDK, Cosmos dash SDK, probably. Yep. So we have this thing called the Cosmos SDK. There's a simple tutorial called the SDK application tutorial. And sometimes we give presentations where we run through it, but pretty easy to run through yourself. Cosmos SDK is great. I've seen a number of teams kind of go from not having a working, or from having a design sketch, an app that was running on an Ethereum testnet, et cetera, and in a week or two having a scalable production-ready Cosmos SDK app. Where I think we have some weaknesses, and that we're going to hopefully sort out over the next couple of months, is that, so this is the server side of a decentralized application, but we don't have great libraries for signing transactions on your phone, querying the blockchain on your phone. It's been nice that actually Binance has built a lot of that stuff, and we just need to kind of actually take the time to fork away the Binance specific stuff and just build Cosmos generic versions of these things. But I'm expecting that to be sorted out in the next month or two. And lots of projects have been able to succeed successfully forge forward just kind of grabbing whatever they could find. But like, yes, I am trying to bring, we as the team are trying to bring order to this madness over the next couple of months. But like, yeah, I mean, the Cosmos SDK mostly works pretty well. You want to build an application, you get proof of stake, governance, economic modeling, all of that stuff for free. Binance started in October, and now it is April, and they're ready to go to mainnet. That's pretty fast time to market. Terra started in like kind of the October, November time. They're also planning to launch in the next month or two. So, we're talking about, Cosmos seems to have pretty effectively demonstrated that our set of tooling brings time to market for blockchain projects to something on the order of 6 months to mainnet, which I think is extraordinarily fast. So these are all the pitches for like why our stuff is good and why you should use it, because it seems to let you build a bunch of super awesome, useful applications. And I'm excited about stuff like what the Near team is doing and what Fluence is doing, because I think all of these things will just add to the optionality. Like, the problem with blockchains is we're such an early stage right now that like, if what you want to build is this, first you have to build consensus, proof of stake, launch like multiple public blockchains, and then get to build this, which is kind of annoying. But like, here we are. Like 3 years after I first drew this protocol on a whiteboard with Jay and Ethan, we actually get to build it. So super exciting. It's been a good year. Thank you.
Thank you, Fluence, Near Protocol, Cosmos, to give us this fantastic speech. And also thank you, the DN, to provide the venue support and the co-host in the event to set up all the equipment here. And thank you, everyone, joining us tonight. And just remember, like, we are ABC blockchain community, and keep an eye on our meetup webpage. So we will post our events there, like real-timely. I think today the event will be end. Thank you.